this morning I presented on the open science badges, or open science digital credentials that we're working on with Mozilla Science Lab. The idea behind this is to collect some sort of structured information on contributorship so that authors can get credit. Researchers kind of a transparent way of communicating and structuring what they're actually doing. But also to better structure the data that we're collecting as publishers and in the publishing research communication ecosystem. So what we've decided is we're working with ORCID, Mozilla Science Lab, and plus Ubiquity wants to be involved to get sort of just off the ground something that's already fairly open source. These badges have already been built. The badge displayer API, badge issuer is all open source. It's already all there. The idea is that we put all this together and we get something, a prototype out there that's useful, that we can go to universities and review committees and say, is this useful to you? What could you do with this kind of information? So the idea is a researcher would submit an article. Once it's accepted, we'd send the DOI as well as all sorts of other metadata to ORCID, who would then send this information, who would look up the ORCID ID of the author and would send this information to our what we're building, which is our badge issuer, our badge kit, paper badger, that's the word. And authors would come together in a sort of matrix and agree on who did what, and this information would then be exported to ORCID and could be, reused in every way that ORCID data is reused. And that's it. Can we get a round of applause?
And I will say that I will tweet out the link so that you guys can see. There's a workflow diagram that we'd love feedback on, and we'll be writing more about it in the next few months as we start to build this out. And so if you followed before going to the Mozilla Science GitHub account, there's something called Paper Badger, and so there's some visuals and some resources there. But extra thanks to Amy for going completely without a computer, not even without a PDF. And so I want to welcome up our next presenter, and this is Michael McLennan from Purdue, who's going to tell us a little bit more about Hub Zero.
Thank you. Yeah, plug in, I guess.
In the meantime, think of really good questions.
Oh, 1,000.
Did we hit the 1,000?
We got to 1,000.
All right.
Julie and Elliot, wherever you are, thank you.
There you go. And your 10 minutes. We'll start as soon as that's live. There you go.
Yeah. Hooray.
There you are.
All right.
He's right here.
So again, I'm Michael McLennan from Purdue University. I want to show you off a little bit about our Hub Zero software platform for scientific collaboration. Hub Zero is free open source software that you can use to create websites, your own websites for e-science that serve photorealistically generated users like that and thousands of other people in the real world in areas like nanotechnology, earthquake mitigation, pharmaceuticals. Each of these different sites, these are all independent websites that were all built with the same Hub Zero toolkit, and each one serves a different community of users, and the users get on and upload their own content. So there are about 60 of these sites now running with Hub Zero, and altogether they serve about 1.8 million visitors every year. And I want to tell you some of their stories. So we start off with a group at Penn State University. They wanted to create a simulation modeling tool that they could use in class to teach nanoparticle optics. So they went on to NanoHub, and under Resources Upload, of course, the NanoHub asks you to sign in if you're going to contribute content. You can register an account and get signed in. You click Get Started, and it asks you what kind of content you want to upload, in this case, tools. So for tools, it asks you a little bit of information. You give a short name for the tool you want to upload and a title for the tool you want to upload. You can decide whether you want your tool to be open source or closed source. You can decide whether there's any export restrictions and put people on the team. So there's a little form that you fill out, and after you do that, you get a Subversion repository, and also you get access to this tool called a workspace. A workspace is a Linux development environment that runs in the cloud, that has all the NanoHub software. You can put anything in this workspace, anything that runs under Linux. So if you have a tool that's written in MATLAB or in Java or Qt or whatever, maybe a commercial tool, you can get it up and running in the workspace. Usually, instead, people come to us with like a Fortran code, and they don't have a good graphical user interface. So they can use this Rapture tool that I'm showing right here to build the graphical user interface for their tool. So you just drag and drop a few controls, like a couple of numbers. This tool takes 2 numbers as inputs and produces a curve as output. I can also add some HTML documentation into the tool that kind of describes it a little bit better. So you can see this is a nanoparticle simulator. There's a particle with 2 material layers. You set the material thicknesses. So you can kind of preview the tool. Under the Tool tab, you can also choose what language this is going to be written in. In this case, it's a Python tool. And when I go to save this tool, I end up saving 2 things. One is an XML file that describes the inputs and the outputs, and the other is a skeleton program for my Python program. So now I can go in and actually edit that skeleton program that got generated for me, and there's all the Rapture gobbledygook that gives you all your inputs. And then there's a comment that says, add your code here. And you just go in and kind of add your Python code into the mix using those inputs and producing the outputs. And then if you say Rapture, voila, it brings up this automatically generated graphical user interface with default values and units. And you just click Simulate, it runs your Python program, you're off to the races. Now the last step is actually to publish this tool for other people to use, and we have a whole kind of content management system that lets you launch the tool so you can preview the tool and see how it's going to work, and if you like it, you click My tool is working properly, I approve it, and then it gets published. So now across the pond, here's another user at Dr. Belitis at the University of Surrey, and he was interested in nanoparticles, and he happened to be searching around on NanoHub looking for extinction efficiencies, which is kind of shining light on it and seeing how the light shines through. And so searching around on NanoHub, he finds all these different resources, including the tool that was published by the Penn State group, really for education. You can see there's hundreds of people using it, a couple of citations, it's been used in class. You can see the DOI too on the tool, and you just click Launch Tool, and again it launches this cloud-based session. This is a little more polished Rapture tool, but you again can very easily specify the input values and run it. You can back up and change the material and run it again, and change the material and run it again. So here's that system with 3 different material types, and you can see the effective material on the optics. You can also look at absorption, scattering. You can mouse over and pull values off the plot. And you can, if you want the data, you just click on the download button, and it'll download all that data that you just generated out of those simulations to your desktop. And then you can take it and put it into your own spreadsheet, or in this case, into your publication. So Dr. Belitis then published this paper that had the NanoHub data along with his experimental data. Now we'll switch gears, and I'll show you about Dr. Sylvie Browder from Purdue University. She went on to the Purdue University Research Repository. This is another Hub Zero instance. This is Purdue's data management solution, institutional data management solution. You can log in, and when you get awarded a new grant, you can create a project area inside of PUR. This is a private area where you can work with your colleagues and share data and work together to create data that you want to publish. You just give it a simple name. You can fill out a little abstract that describes the project in case somebody sees it and they wonder what it is. You can upload an image file that kind of represents the project. That's good when you start getting 10 or 20 of them. You can easily tell them apart. And then down at the bottom, you can see you have choices. You can keep the project completely hidden if you don't want anybody to know about it, or you can make it so that anybody can at least see the abstract and they can see it on the site. But of course, you can't see anything inside the project unless you're a member of the project. So here's where I'm inviting in the members of my research team. I'm typing in names, and if people have already been on the site, they pop up. If someone hasn't yet been on the site, you can just type their email address, and then they'll get an invitation, and they can join and join the site and come to the project. So that's the team for now. I can invite more people later. Now, this particular site has one more form in here. We put this form in for the sponsored research people. They like to keep data on which award this is attached to and all of that. So there's a little extra. And you also have to agree to the terms and conditions. And voila, now we have a project area. So now you can work together in this private space with your group. It has kind of a Facebook-style wall on the outside, so you can post updates. It also has a file repository that you can upload your data into. This is based on Git, so basically it's a Git repository under the hood with a nice web-based interface. So I can choose my CSV file and upload that into the Git repository. You can, of course, choose multiple files at once if you want to. You can also upload a zip file. If you upload a zip file, then it asks you if you want to expand the zip file. And in that case, I said yes, so it's going to put a bunch of data in all at once. You notice up in the corner, too, you can connect it with Google Drive, so you can actually sync this all to your desktop if you like using Google Drive. It's another way. Now, we're going to create a database. We're going to take that CSV file that I uploaded and convert it automatically into a MySQL table with this nice JavaScript interface that lets me, in this case, annotate. It guessed a lot of the things. It guessed which columns are integers and which are floating points, but I can change that, and I can add descriptions to all the columns. I can add units of measurement. I can change colors and things to kind of make it more comprehensible. And now I can save this data table at first for the people in my project so that they can all check it out and work on it. So I'm describing this right now for the people in my project and have them take a look first. So here's my database. And you can see there's also controls. We can update the database. Of course, there's going to be errors, and we have everybody on the team look at the database and update it. Or we can add more databases and so forth. And this is what we see for now in our preview mode. Ultimately, this is what will get published. The whole end goal of this is to publish that as a publicly available data set. But there's a lot of work to do in the meantime with the team, so I'm going to create some to-do list items. So this to-do list item is a little post-it note, and I can assign that to someone else on the team and give it a due date and say, hey, help me out here, fill in some of the blank data from the old data sets that we used to have. And he may post a comment saying, what are you talking about? I don't see any blank spots. And we can go back and forth and kind of discuss it until ultimately we check it off and get it done. So you might have a little bit of project management stuff. And you see all of this is being posted on that update feed too automatically. So you can see what's happening in the project even if you didn't post the updates explicitly. Now let's shift gears and see what a published data set looks like. There was a team that went down to Port-au-Prince, Haiti to survey all the damage from the Haiti earthquake in 2010. And their data set is now published on nice.org. So if you search for Haiti earthquake database, you can see the team, you can see some of the damage, the citation instructions, and if you click the button, it takes you right to the live data set. And you can interact with the data set. I can say, show me all the buildings with greater than 6,000 square feet and sort in order of reinforced concrete damage. So these are the ones that had the most reinforced concrete damage and are the biggest buildings. So you can actually interact with that data. So that's just kind of a brief less than 10-minute view of what's in Hub Zero. I hope you guys will check it out, download the software, and create your own site just like that. Thanks.
And unfortunately, Amy had to run off, and we should have done this at the end of there. But while we switch laptops, and Francesca, if you can come on up. While we switch laptops, does anyone have a question for Michael about Hub Zero? Anyone? Anyone? And there'll be time for more questions at the end if we all keep on time.
Hey, Michael, that was a really impressive presentation. Thank you so much. Count me in. What's your biggest implementation? How many rows? I don't even know how you'd quantify it.
In terms of a single database, you're saying?
Yeah, of all your 60 instances, how many records? What's your max? Because I'm wondering how well it scales up.
Yeah,
for big science projects.
Yeah, so I would say in terms of big data, the big axis that we've actually tackled of the 4 V's is the variety one. We handle variety much better than we do volume or velocity. The biggest table we have, one of them is on PharmaHub. It's an excipients database that has a lot of different excipients from pharmaceutical manufacturer, about 30 tables, but really it's only thousands of records. It's not millions and it's not big data in the conventional sense.
Is there a reason why it couldn't go into...
No, there really is no reason. We're always driven by projects and the demands, and so there are lots of projects going on, and the ones that we've been engaged with, usually the ones that have big data requirements, like astronomy, they've already got their own solution. So people tend to come to us when they're not in astronomy and they need, yeah, we're in kind of the long tail. Yeah, thank you.
Thank you again. And on to the next presentation. This is Francesco Osborne from Open University UK, who will be telling us more about, is it RExplore?
Yes.
Or Rexplore? Do you want to be Rexplore?
Rexplore.
Okay, I'll hand it over to him. Your 10 minutes starts now.
So thank you very much. Yes, I will talk to you about our system, Explore, and in particular some data analytics that our system can do. But actually we will focus in this 10 minutes on a particular part of our system. So in particular, I will start with a pretty big claim. That is, I don't think that we understand well our search work. Sure, we understand the scientific method, and you know, the room is full of talented researchers that can address our research problem and try to find a solution. But the thing is that today research is made by network of researchers that interact together. So when we explore this world, well, the key is the community. I heard in this day that many people were talking again and again about community. We are a community. We should integrate with other community. We should communicate with other community and so on. So community are a very important part of the research environment that are usually neglected. We do some data analytics on them, but we don't really understand them so well. So we'll show you how can we do something better to understand this kind of community. But first, why we want to understand community. The first thing that is very important that community do is that community usually have a goal. Community have a vision and they try to implement it in some way. And to be successful, these people should networking in an efficient way. So an example I'm very fond of, you may know linked data is a very popular technology today. But to go and to be able to build the linked data technology, there were a series of groups or community that worked on complementary problems. So some people built a data set, some people built Sparkle, that is the engine for querying linked data, other people work on other kind of semantic annotation, and finally we were able to have the linked data technology. And the second thing that we want to do is to try to understand what is the relationship between the research community and the real world, in the sense which are the discoveries that really change the economical situation or the social situation, and on the other side, which are the technological breakout or the social breakout that change research. Another example, here you can see in 2006 is the year in which the iPod came up. What happened is that a lot of research community changed a lot. Many of them forked a second community that was just focusing on some mobile version of the previous community. So for example, the people from the virtual reality community started to work on mobile device and augmented reality. So how can we try to decipher the code of research community? Usually when you think about community, you think about a network of researchers. This, for example, is a network of researchers in the semantic web. However, this kind of vision is, this kind of visualization is not very helpful to you. If you don't know the semantic web, these are just a bunch of names. What our system is able to do is to find the community within a certain area, for example, the semantic web, and have this more sophisticated visualization that will tell you, semantic web is a wide area. Inside the semantic web, you have a group of authors working on different kind of topic, on complementary theme. Usually they have the same vision, sometimes they take different approaches, sometimes they have different sub-goals. And then you can relate this community to authors, or in this case, to organization. And with this kind of representation, you can really start to have a more comprehensive idea of how a research area is evolving in time, because you can see all these subgroups that are connected with each other. So I will show you briefly some piece of technology that we've developed. Mainly this community are built by Random community detection or a clustering algorithm over a social network of authors. Actually, we do something completely different. That is, we search for authors that have the same trajectory. All the authors that come from topic A, then went to topic B, then went to topic C. And actually, for doing so, we cannot take the same topic as many applications. Many applications take keyword explicitly for a search topic, but that's not very effective because different authors will use different names. So actually, we use a bunch of semantic magic, and what we do is that actually we cluster together authors that work at semantically correlated topic at the same time. And for doing so, we develop an algorithm that is called Clink that will automatically build for you a classification of a search topic. So if you have just a flat list of keywords, what you can do is to build this classification that can be in form of taxonomy or OL ontology, and you will be able to look at this topic and understand how similar they are according to their semantic relationship. So, for example, linked data, you know that is a subtopic of semantic web. And in this way, you can build different kind of community, but these are not good enough yet because they are very static. So what are we working now is to build systems that are able to visualize community diachronically. That is to see the evolution of community in time, how they change and how they evolve their trends. So basically, we should do two steps. The first one is that we use statistical technique to try to understand how change the distribution of topic in the different year. And so, for example, you see that the community that does information extraction in the year 2000 was mostly around natural language, while today is mostly around semantic technology. And the other thing that we can do is to look which community interact with each other, which are the subgroups that are talking, and maybe they are producing something new because they are able to exchange knowledge. And we do so by detecting a number of events like to community splitting, community merging, community forking, and so on. So I will show you some final result. So this is, for example, the map of www, and you can see that we have a number of subgroups that work on separate problems that in the end, they work more or less all on the common vision of www, and you can see in this case how this community changed in time. So, for example, the community of internet services then started to work on peer-to-peer and so on, distributed computer today, and you can see Facebook in the sense that if you could look in the year 2006, you will see that suddenly the social network community pop-ups. And first, it's just a community about user behavior. Let's try to understand with social network how users interact together. And after a few years, people from the data mining community come inside and start to do more and more data mining. So the nice thing about this is that you can really explore, and this is the semantic web, for example, you can really explore the history of an area and try to understand how the different group works together. Why? Well, one thing that we want to do is to understand if we can learn good lesson. Before I mentioned the good story of linked data. So can we replicate the story of linked data if we believe this is a good story? Can a community that have a similar goals look at the way this author interact and address different tasks and replicate this kind of success? And at the same way, can we look at the history in which we were unable to do what we wanted to do and see what were the errors of the past? So I think that we should try to look more and more at our research community because research today is becoming a network problem. And so we should understand the characteristics of this network. We should understand the rules of this network for trying to understand how research works. Now, I will show you briefly some image of what can Explore do. 2 minutes? 2 minutes are more than enough. So for example, here you can see nothing. But here you can see something. So here you can see briefly Explore how it works. So Explore is a tool that integrates a lot of research entities. We have authors, we have communities, we have different kind of groups, and this should play. Okay, it's playing. Different kind of groups, and the idea is that you have a tool that is as simple as a Microsoft Academic Search or a Google Scholar, but allow you, for example, to do very complex search on authors and on organization and our research community. Here, for example, you can see that the user is filtering the graph over Rico Motta. Rico Motta is my professor, and thanks to this tool, we can look at these different connections. We can filter them by using different topics. We can look at the community that Rico is active inside, and basically we can understand much better how the different research entities interact with each other. So, 10 seconds. Well, I don't need a slide for 10 seconds. So basically what I'm trying to say is that look at Explore, of course, but if you can, try to look more and more about the research community, because I think research community are the entity that we should really look at in the future to try to understand which are the rules of research and how we can interact in a more efficient way. So, thank you very much.
He was 1 second away from the duck that was going to quack to tell me that we were 10 minutes. Thank you for that. While we get Henry all set up, does anyone have any questions for Francesco? I'm going to look at Clem on that side, yeah?
What kind of data does it plug into? I'm here.
Oh, he's over on this side right here.
Okay, sorry.
Can you say that one more time?
What kind of bibliometric data do you need to run that? Like what?
Not so much. Actually, Explore is agnostic with respect to the data, and basically you need to just metadata about paper. So it takes metadata about paper that is like title, abstract, author, and so on. So the simple data, and it builds everything. It builds authors, it builds community, it builds affiliation and then organization, it builds group representing university and group of authors interacting together. So it needs just this minimal thing, and then it does all the data analytics. And it tries to do it in a way that normal people can do it. People that is not interested in data analytics itself, but can use the result of the data analytics.
Thank you again. And next up, we have Henry Zherpa. How'd I do? Is that okay? Henry Zherpa. Anyone that's looking to know what the Polish for turnip is, apparently I've been told today that that's Zherpa. So Henry is from Imperial College London, and he'll be talking about interoperability of data repositories. So Henry, the floor is yours.
Thank you. I'm going to need 3 hands here, so just watch me sprout another hand. Actually, I'm not the geek. This is a geek session. Nick, you're the geek. Stand up. This is his project, so take a bow, Nick. I'm just going to explain it to you, if I can find a hand. Also, chemists do things differently. Welcome to the wonderful world of molecules. I think I'm the first lecturer to use a green laser pointer this week, so that's... If you ever see a green laser pointer, it's almost certainly a chemist. Right, I did try to become a non-chemist by buying a blue laser pointer, but that didn't work. There's a little bit of, that's the string, if anybody wants to tweet it. I haven't tweeted it, but you can tweet that. And this is our culture. This is basically how we operate. If you do want to learn about what chemists do for a profession, some of that is there. I've got all the right jargon at the beginning as well. So I'm going to start with a hero, because we heard someone earlier today, I think, talk that we have to mention our heroes in data. And this is one of the heroes in chemistry, Konrad Beilstein, 1881. He decided to document all the known data about all the known molecules in 1881. And he did it in 2 volumes, which he published. And there are about 5,000 molecules and perhaps 5 or 10 data points, so it wasn't quite as grand a thing as you might imagine. Nowadays, the custodian of that is this company here, so you do actually have to pay, nowadays, have to pay these guys to get the same data for about 100 million molecules, which is what we've reached in 2015. But my point is that most of the data in modern times isn't captured. We think that about 80% of all research data in chemistry is lost, and even a thesis probably doesn't contain it. I don't know if Mark Hunnell is here still. No, he isn't. Yes. Yeah, right. Is that statement correct?
Yeah, more than 50.
More than 50. I just guessed 50. I wasn't going to be out by more than 50%. So what would you reckon the percentage was that you could not put into your thesis?
Mine was like 90.
90% of what he collected over 3 years well, I mean, you eventually put into Figshare, I guess, did you? Something. Anyway, that's the problem. Now, my central question is, what are the publishers doing to help us solve that problem? So, this is what they're doing. This is totally randomly selected. They don't call it data, they called it supporting information. Somewhere in there, that's the supporting information tag. There it is. They don't tell you the format, which is nicely blank. They're too embarrassed to confess that it's a PDF. It doesn't actually have a format, but they could leave that blank. And the description, if those of us who like metadata, would be called miscellaneous information. Really tells you a lot. So that's not a good start. I want to expand what you just saw into a readable form. This red text is what you saw in the previous one. I could probably talk for half an hour on what's wrong or what's unhelpful about this statement. Virtually every phrase is noteworthy. I noticed just one. They assert that the supporting information, which is where all of Mark's data would have gone, is peer-reviewed. Now, it's 100, 200 pages long. I really don't believe that statement. I don't think it's peer-reviewed, but they claim it is. There's lots of other stuff, basically, that one could talk about there. Right. Those are the issues. So what's our solution? Well, I mean, I think we've heard this solution many times. It's not our solution, it's the community solution. We think a greater separation of what we call the narrative, the story about chemistry, from the data, and that each of these objects should be held in a sort of place where it's best suited for. The narrative is still held in journals, perhaps, although today, from what we've heard, maybe even that isn't true. And the data should be held in data repositories, and we've heard many examples of that. Each should be addressed by persistent identifiers. We've heard a lot about that. And we should really struggle, or really work hard on the metadata. So DOI is everywhere, standards everywhere. So what do I mean by standards? And that's what I mean by interoperable. So these are some of the standards that we've identified to help us fix this problem. So persistent identifiers, something called a crosswalk, which is a metadata schema or a metadata schema mapping between wherever you hold the data off to, say, another organization such as DataCite. And so a lot of these things we've heard. ORCID has been talked about a lot. ORE and METS, their standards. Some media types, we've heard about that. And one that I think has not been sufficiently recognized, this should be live. And so that's a live resolution. That's just a DOI, as you saw. But if you subject it to the DOI agency, you get all this information, all these bit streams about the files and how to get them. This is all priceless stuff because it enables you to get access to this stuff. That's just the standard DOI. We've added that, basically. We've added this information. So the message from all of this is fair data should be accessed and reusable simply by knowing its persistent identifier, which in this case is a DOI. This gives us programmatic access directly to the data, and the benefits and lots and lots of things can accrue from that technology. So these are the demos. I showed you that first one. So this is 3 different ways of loading a molecule. So if you've never seen a molecule, here it is. I once showed, many years ago, this kind of display to a politician who had come from the House of Lords in Britain. And this molecule was prancing around, and he considered it, and he was quite serious. Gee, I never knew they were that big. And he wasn't joking. Anyway, load up a molecule. That went off to the repository, and there it is. And you can see this thing gently rotating, and you can manipulate it, and there's lots of menus you can thing, and so on. So that's a good tool for looking at molecules. So that's that method. That's another bit of technology, all standard stuff. This is, again, an underused method that DataCite themselves developed called the Media API. We load that. Again, it's doing a query. Oh, goes to get a different molecule. There we are, again, just to prove that it really is a real molecule. So they're not really that big, in case anybody was wondering what I meant by that. They're a bit smaller. Another set of standards. So this is all basically, you just read the documentation until you're sick and tired of it. How many months did you read documentation for, Nick? many months, not too long. So this is now programmatic because you have to put some JavaScript program behind it to make it work. This simply tells you what data is available, or you can bypass the data and go directly to one of those entries, or this one here. I'm amazed at how quickly this works, because this is a live demo and we are going through. It's not being videoed and recorded and canned. So 2 concluding remarks. 2 minutes, wow, okay. I added this today because I read you wanted the scholarship that had emerged from all of this, and I hadn't done that. But if you want to explore it, here's some papers that we've published in 1914, and essentially the standard paper is referenced here, and to each of these is added this thing called data, sometimes many bits of data, and so each of these represents the data associated with the article. The article is held in a journal, the data is held in a data repository. We're hoping to make a more formal linkage between these two. At the moment the linkage is this page, but we're talking to Dryad and other people about actually doing a bit better than that. So that's the scholarship. All those prancing wonderful molecules which help us understand it. And one final bit of kind of future-looking thing, by doing it this way and applying all those wonderful standards, you can construct a search query of this type. This is a real search query, and I'll do it live in a minute just to prove that it's real. But essentially what it says is we want various alternate identifiers. In other words, each community names its objects differently, and chemistry is no exception. There are 6 different identifiers for a particular model, including the DOI. There's the NCI identifier, and all of these. If you're a chemist, you might know about some of these. And so these are all identifiers, and they're all searchable and exposed through DataCite. I'm actually going to click this live. It's actually returning 10 molecules, but it wouldn't take much longer to return 250,000 if you really wanted to. And these are all these entries. You can process them in whatever way. So we think that the bottom line is, whenever there's a standard, do please try to use the standard. They're there for a purpose. We were amazed that 2 of the 3 standards that I've talked about are almost completely unexploited. There were about 8 instances of these standards for the second type, until we added another 150,000 on DataCite. There are no instances of the first type that we're aware of, the LOCAT type. And the third one, I don't know of any implementations either. So I think the bottom line is, if you do things with standards, all sorts of fun things emerge. Thank you.
So while, Matt, I don't know if you want to come and set yourself up. Any questions for Henry? Has everybody fallen asleep after the tea? No. Okay. Well, we will save some time for him. Oh, we got it.
So what stack would you recommend for implementing a molecular viewer today?
What stack? I mean,
yeah.
We've heard a lot about communities today, and there is a remarkable unsung community. It started off in chemistry. It was known as the JMOL community. They've now abandoned Java and gone over to JavaScript, so they're now called the JSMOL community. But in fact, they're not restricted to chemistry. They're material science, physics, mathematics. And this community, perhaps of about 100 active people, led by a chap called Bob Hansen. The community's been active for 25 years. The viewer that you saw is JSMOL. It's any sort of 3D object that can be expressed in a standard way can be rendered in this way. And the community was just amazed at how other communities used this particular tool for their own visualization. And vice versa. I'm sure there's other tools that we use as chemists that are part of other communities. So JSMOL is the community. Just Google it and you'll find it.
Thank you very much, Henry. And also thank you to Nick in the audience. And finally, to wrap up the demos, we have Matthew Cockrell, who's going to be telling us a little bit more about Riffin.
Thanks, Caitlin. So yeah, I'm going to tell you about Riffin, which is a new tool we're building to try to deliver increased reproducibility to lab research. So what's the problem which Riffin is trying to solve? Well, we know that reproducibility is an issue in research. And our contention at Riffin is that a lot of this reflects the problem that the current approach to doing experiments is very much the blacksmith shop approach, the sort of pre-industrial revolution approach. It's very ad hoc. A lot of information is implicit, is passed on indirectly, and as a result, you don't have solid reproducible foundations. This causes issues in academia, in that for basic research, the results which are published are not reliable, and as a result, the funders are spending money which is not wisely spent and is attempting to reproduce things or build on things which aren't sound. And even more directly, in industry, R&D is not as effective as it could be, and companies see this problem that it takes longer, and they have failures to translate academic advances into practical benefits. So to see how this sort of looks, this is a real-world example of how R&D processes operate in industry. And this was a napkin sketch, which was the way in which an update to an R&D process went through to scale up a manufacturing. And Riffin's been speaking to a bunch of companies doing R&D in biotech on both sides of the Atlantic. And it's really surprising in a way just how much of an issue this is, and not having good tools to deal with the rapidly changing R&D environment and the different sorts of experiments being done, and how to capture the process details along with the data so that issues can be tracked down, the root causes of problems, the root causes of failures to upscale or translate things can be rapidly identified. And Riffin aims to solve that. We're taking lessons from the world of manufacturing. Now, manufacturing is in some ways a simpler problem. It's sort of based around standardizing things and trying to just make those things keep working reliably. But that was a challenge, right? In the 1960s, automobile manufacturing produced lots of cars which came off the end of the line and just didn't work. And it took a lot of work to build those cars. The Japanese in particular applied a bunch of ideas to actually tracing the root causes of quality problems systematically, and those produced dramatic results in terms of increased productivity and a reduction in the number of faults coming off the end of the line. And that was a hugely important competitive weapon for them in terms of developing their industry. So there are lessons from the improvements in manufacturing that can translate back to R&D. So one of the things which we see is applying very much to the experimental process is that everything in manufacturing these days starts from CAD files, computer-aided design files, and it means that you know what it was that you plan to build and what you plan to make, and if you want to go back and tweak it and compare the results, you know what you're comparing with. And the problem with a lot of the way experiments are done is you don't have that reference point for exactly what the previous researcher did. And those can be very, very complex, but you can manage that complexity with modularity. You have very, very highly instrumented setups, so you're capturing lots of data, not just necessarily the final end result, but capturing data along the way so that when problems arise, you can figure out, oh, it always happens on a Wednesday, or it always happens when it's a bit warm in the facility. And that needs to be automated. You then need to have processes where you go around and continuously look for opportunities to improve processes. And you might think that in an academic environment, it's not like that. You don't just do the same process again and again and again. But actually, all the different experiments that are being done in academic labs are making use of the same assays and sub-processes, just in different combinations. And so having a system in place to be able to learn from what works and what doesn't and make it work reliably can apply there as well. And then another thing, which is very big in this kind of manufacturing process, is making everybody contribute towards that wider goal and having transparency about data. So it's not just looking for the good data and making that visible, but it's having all the problems visible throughout the process so you can identify the root causes and fix them. So that, yeah, in terms of R&D, this matters because if you can get this sort of quality in R&D, you can build forwards much more effectively on solid foundations. This is an example of the real-world impact of this in biotech. This upwards graph is to do with a synthetic biology company looking to improve the yield from its fermentation process to produce a particular chemical. And in the early days, the bottom part of the graph, the noise in the assays they were doing to establish which were the best strains was so significant that the only very, very big jumps were possible. They couldn't spot the small improvements because they were hidden in the layers of noise, so they would find themselves chasing things which looked like improvements which weren't. but just purely by improving the IT systems and the data analysis, capturing more data so that they could see what was noise and what was signal, they were able to capture smaller improvements and then more rapidly increment and go through the cycles to add lots of small improvements. And those combination of lots of small improvements, as you can see, increased the rate of improvement by about twofold. So existing lab software doesn't really address this problem. There are a couple of kind of widespread things used in labs. Electronic lab notebooks, which tend to be quite unstructured and simply provide a more searchable, convenient alternative to a paper lab notebook. And then there are highly structured lab information systems, which have the benefit of adding some structure to the data and capturing data in one place, but tend to be very highly specialized to a particular type of experiment and a particular type of data. And it's very expensive and very hard work and complex and takes a lot of time to adapt them to new sources of data and new processes. And so the goal with Riffin is to make that change of process be an inherent part of the day-to-day usage of the lab system, rather than something that's only done every year or so by an IT project. So Riffin is a cloud-based software platform, and it's really designed to be computer-aided design for experiments, to put the design of experiments at the heart of R&D. And so and together with that, having designed the experiment, data streams then get captured, and ultimately the researcher ends up with a unified historical view of all their experimental processes and all their data. And the benefits of doing this is that you can do your analytics and visualization not just on these silos of individual bits of data, but also on the process context they came from. Increasing the signal-to-noise ratio, so you've got a clearer sense of what matters. You can make your own changes to the process very flexibly, and then all of the processes are shareable and versionable using things like GitHub. And the idea here is to make all of this process description so that it's based on open standard format, so it's interoperable with other tools. And so just to summarize the approach, it reflects the cycle of iterative improvement of doing research. So there's a design phase where you build the protocols using a web-based process designer, then a phase where you can annotate those process designs with the data capture points, automated analysis and error checking, and root cause analysis based on those data streams, with the ability also to export to external tools for analysis, and finally its ability to flexibly share any aspect of the process, whether via a data repository or via a journal. So I guess I haven't got time to show you any of the nice screenshots of what we're building, but you get the basic idea, and I'm happy to answer any questions about it.
Show at least one screenshot.
Okay,
come on.
so let's just go. 2 minutes, okay, well, it's been waved at about time, but hey. Okay, so this is a kind of example. These are still, we're still talking early days right now, so these are slightly more than mock-ups, but not yet a fully functional system. But you can have the idea of this process flow is it's fully hierarchical, so you can simplify it down by wrapping an entire flow into one box, or you can drill down into that box and expand it. So it's like Lego, you can have units to build up complex processes. Lots of quantitative data which can go into those, then you capture the data streams which can come from, I should say, any of these 4 sources. So directly from instrument APIs, from the file system where they're already being dumped into by different instruments, from a database query if you have a LIMS which has brought together all of your database stuff, or for the stuff which is just on pieces of paper in the interim, you can just drop that stuff in as well. And it all feeds into this big picture of all your experimental process details and all of your data streams. And little thing to make sure that things aren't left offline. Nice thing about the really cheap Internet of Things devices right now, you can take all your legacy systems from the 1980s, plug in a serial port attached to a little Wi-Fi device, and we'll be working with open source drivers to try and make sure that every single device in your lab is fully connected into the Riffin ecosystem. Okay?
Any questions for Matt?
Just how expressive do you plan to make the Lego-like language for describing protocols?
It's an interesting one in terms of there are different things where this either is being done or has been done. So one of the things, we don't want to reinvent the wheel here. And so, for example, in the areas of synthetic biology, there are process control and description languages which are going into this area quite a bit. Finding the right sweet spot is difficult, and so we're working with different specific use cases, but trying to make them broad enough that we can do something general as well. So, I think the idea is that it should be, by virtue of the hierarchicalness, have the potential to drill down to a very, very fine level of granularity. But we also don't want to mean that the requirement in order to get started to do anything is that you have to do an immense amount of work to kind of create your toolbox of Lego to start with. So I think the idea is you could start using it with a relatively simple model of your process, which is high-level units. So for example, we're looking at people using computational workflow pipelines with Galaxy. You could just say that acts as one block within our system. You can drill down into Galaxy to find out more about what's going on within it. So I think the idea is over time we want to allow this to evolve greater sophistication, but we think a lot of value could come from it with a relatively simple process workflow model initially.
Okay. Can we get another round of applause for all of the demos? And also we're saying for all of the other submissions, there were a number of submissions for the demos that we sifted through, and it was really difficult to make that decision to get down to 5. But also a thank you to everyone that submitted a poster and was presenting over the last few days. So another round of applause for everyone with posters.